Welcome back to the deep dive. Today's going to be a bit of an experiment for us.
A little bit, yeah.
Usually we're wading through, a stack of heavy academic papers or deconstructing some controversial op-ed. But today we're taking a source that, on the surface, looks like a coffee table book.
It does.
It's a collection from the Smithsonian called Did You Know? Amazing Answers to Questions You Ask.
And I can just see the skeptics rolling their eyes already. I mean, it looks like a kid's Q&A book. It's colorful. It's got these huge, beautiful pictures. But, and this is a really big but, when you actually read the text, it is deceptively dense.
That's exactly why I wanted to do this. We often assume that deep means academic jargon.
Right, inaccessible.
Exactly. But this book manages to take these simple questions. I mean, the kind of 6-year-old would ask you, like, why is the sun hot? Or where did the moon come from? And the answers, they force you to confront some of the most complex physics and geology in the known universe.
It's the Feynman principle, isn't it? If you can't explain something simply, you probably don't understand it well enough. This book explains it simply, which means the underlying concepts are just rock solid. It's a roadmap of scale.
That is our mission today. We are going to follow that roadmap.
A galactic roadmap.
A galactic roadmap, yeah. We are going to travel from the supermassive black hole at the very center of our galaxy, zoom out through the spiral arms, make a pit stop at the sun.
Take a tour of the planets.
Specifically the weird ones. Then we'll land a rover on Mars and then, crash land back on Earth.
It's a journey from the macro to the micro, really. From 13 billion years of cosmic history down to the, 1.5 inches, the moon drifts away from us every single year.
It's incredible. So before we fire up the engines, I want to pose 3 questions to you, the listener. These are the hooks that really got me.
Okay.
1, if I snap my fingers and the sun just goes out, we all know it takes 8 minutes for us on Earth to go dark, but how long did that light spend trying to get out of the sun before it even started that 8-minute journey?
Oh, the answer to that is genuinely disturbing.
Yeah.
It's one of my favorite facts.
Right. Okay, 2. Why is Venus the rebel of the solar system? It's doing something fundamentally different from all the other planets.
The odd one out.
And 3, if you were driving the Mars Curiosity rover and you just floored pedal to the metal, would you get a speeding ticket?
You wouldn't even get a walking ticket. Not even close.
Okay, let's start at the beginning. Or I guess let's start at the center. Section 1, the galactic context. The book opens with this really simple question: how many stars are there? But it very quickly pivots to describing our home turf, the Milky Way.
And we really need to correct a common mental image here. When most people think of a galaxy, they picture that perfect, symmetrical whirlpool,
Like water draining in a sink.
Exactly. Uniform, swirling arms. But the Smithsonian text specifies that the Milky Way is a barred spiral.
Okay, let's unpack barred. Because when I hear that, I'm picturing a prison cell or maybe a pub. What does a bar actually look like on a galactic scale?
So imagine that whirlpool again. But instead of the arms spiraling directly from that tiny center point, imagine a straight line of stars. A huge glowing rod that cuts right through the center.
A rod of stars?
A dense rod of stars. And the spiral arms, they don't start at the center. They trail off the ends of that rod.
So it's more like a pinwheel with a straight piece in the middle.
That's a great way to put it. It gives the galaxy a much more distinct architectural look. If you could fly above the Milky Way and look down, which, by the way, would take you millions of years just to get to that vantage point, it would look like a glittering wheel, as the text describes.
But we can't do that, can we? We're stuck inside it, which is why, from here on Earth, all we see is that sort of milky, hazy band of light across the night sky.
Exactly. We are looking through the disk, edge on. I like to use the pizza analogy. Imagine we're a single pepperoni slice, maybe halfway out from the center.
Okay.
If you look toward the center of the pizza, you don't see the whole circle. You just see a long, dense line of cheese and crust and other toppings.
You're just seeing the cross-section.
You're seeing the cross-section. That's our view of the galactic core.
And the scale of this pizza, the text just casually says hundreds of billions of stars.
Hundreds of billions, and that's just our pizza.
Right.
The text reminds us there are trillions with a T more galaxies out there. It makes you think of the Hubble Deep Field image,
Oh, yeah.
You point a telescope at a patch of what looks like empty black sky, a patch the size of a grain of sand held at arm's length. And in that one tiny speck, you find 3,000 galaxies.
3,000 galaxies and a grain of sand. It effectively renders the human ego null and void.
It absolutely should. It really, really should.
So what's holding this glittering wheel together? The text mentions a hidden center.
A black hole. Sagittarius A star, to be precise. A supermassive black hole.
And why hidden? Is it just because it's, black, light can't escape?
Well, yes, that's part of it. Light can't escape it, so you can't see it directly.
Hmm.
But it's also literally hidden by thick clouds of gas and dust. The galaxy is a dirty place. The text mentions these huge clouds, we call them nebulae, that drift between the arms. These are the star nurseries. That's where new stars are being born right now.
So the galaxy isn't just a static, beautiful structure. It's an engine.
Or a garden, maybe. You have stars being born in the nebulae, and you have old stars dying, going supernova, and seeding the next generation.
Speaking of old stars, the source drops a number that I had to read a few times. The oldest known star is 13.2 billion years old.
Methusela star.
Yeah, hold on a second. The universe itself is estimated to be, 13.8 billion years old?
That's right.
So this star formed almost immediately after the Big Bang.
Cosmologically speaking, yes. It formed just 600 million years after the Big Bang. That star has witnessed the entire formation of the Milky Way. It saw the birth of our own sun. It saw the rise of life on Earth. And it is still burning out there. It's a genuine relic.
A time capsule from the dawn of everything.
Yes.
And on the other end of that spectrum, you have the sheer size of some stars. The text classifies the biggest ones as supergiants.
And supergiants are, they're terrifyingly large.
How large?
Well, if you took a supergiant like Betelgeuse and dropped it into the center of our solar system where our sun is,
Okay.
it wouldn't just swallow the sun, it would swallow Mercury, Venus, Earth, Mars, and its outer edges would probably be licking at the orbit of Jupiter.
Just one star.
Just one star, the size of our inner solar system.
Wow. Okay, that is a perfect transition to our own star. We need to talk about the engine of our little neighborhood. Section 2, the sun.
The star we can actually feel.
The book asks, why is the sun hot? Which feels like a question a toddler asks right before they touch the stove. But the anatomy lesson it gives is crucial. It says the sun isn't solid, it's a mixture of hydrogen and helium gases.
It's plasma, really, a superheated state of matter.
Uh-huh.
And we have to distinguish between the core and the surface. This is where the physics gets incredibly intense.
Let's just look at the numbers here. The core, 27 million degrees Fahrenheit. That's 15 million Celsius.
That is the fusion reactor. That is where hydrogen atoms are being crushed together under such immense gravity and pressure that they fuse into helium. And in that process, they release a tremendous amount of energy.
So it's a nuclear bomb.
It's a nuclear bomb going off constantly in every direction, held together by its own immense gravity.
And the surface,
By comparison,
much, much cooler. Only about 10,000 degrees Fahrenheit.
still hot enough to vaporize a car in an instant, but compared to 27 million, it's an ice cube.
Relatively speaking, yes. And the text has a great description of the surface. It calls it grainy.
Yeah, what does that mean? Is it like sand? Is it textured?
No, think of a pot of boiling oatmeal.
Okay.
You know how you see those bubbles rise up, bring heat to the surface, they pop, and then the cooler oatmeal on top sinks back down.
Right, that rolling boil. That is exactly what the sun's surface is doing on a massive scale. Those grains are convection cells of hot gas, each one about the size of Texas, bubbling up to the surface.
A Texas-sized bubble of plasma. That's a terrifying image. And then you have the dark spots on the surface. Sunspots.
Which are just cooler patches.
Yeah.
And I use cooler in quotes. They're still incredibly hot. They just look dark by comparison.
Yeah, why are they cooler?
It's where the sun's magnetic field lines get twisted up and burst through the surface. They're so strong they actually stop that bubbling action, that convection. So the heat from below gets trapped, making the surface spot look dark.
Okay, I have to stop you on this next number because my brain is just rejecting it. This was my aha moment of the whole week.
This is the one.
This is the one. We learn in grade school light travels at 186,000 miles per second. It takes 8 minutes to get from the sun to Earth. A snap of a finger in cosmic terms.
Right.
But the text says the energy takes 100,000 years to get from the core to the surface. 100,000 years. If light is the fastest thing in the universe, how can it get stuck inside the sun for that long? Is it getting lost?
It's not getting lost. It's getting mugged.
Yeah.
Repeatedly for millennia.
A mug.
Think about it this way. The core of the sun isn't like a room filled with air where light can just travel freely. It is incredibly, unbelievably densely packed with plasma. It is 150 times denser than water.
So it's like trying to run through a brick wall.
It's much worse than that. Imagine you're trying to run across a crowded football stadium, but the stadium is packed shoulder to shoulder with people, and every single person is blindfolded and just running in random directions.
That's just chaos. Pure chaos.
Pure chaos. Every time a photon, which is a little packet of light energy, is created in that fusion reaction, it moves a tiny fraction of a millimeter before wham, crashes into a charged particle, an electron or a proton.
And what happens?
It gets absorbed and then it gets re-emitted. But here is the kicker. It gets re-emitted in a totally random direction.
So it could be sent backward, back toward the center it just came from.
Exactly. It could go sideways. It could go backwards. It's taking 2 steps forward, 1 step back, 3 steps sideways, another step back. It's what physicists call the random walk, or sometimes the drunkard's walk.
So it's just pinballing.
It's pinballing its way through the core, frantically trying to escape for tens of thousands, up to 100,000 years.
That completely reframes the sunlight that's coming through my window right now.
It should. That light on your face. The energy that makes up that light was technically born during the last ice age.
Wow.
It spent 100,000 years fighting its way out of the crowded stadium of the sun's core. And then, only once it finally broke free of the surface, did it get to enjoy a nice, peaceful 8-minute sprint to Earth.
That is profound. It's not just a light bulb in the sky, it's a time capsule.
It really is. And the sun isn't just glowing, it's incredibly active. The text mentions these huge loops.
Giant loops of glowing gas shooting out into space.
These are coronal loops. They follow the sun's magnetic field lines arcing out and back down. And the text notes they can last for months. Imagine a tornado made of fire that is larger than the entire planet Earth, and it just hangs there in space for 3 months.
And we also get a nice, simple explanation of eclipses. You know, the moon blocking the sun.
Total solar eclipses are a beautiful, beautiful cosmic coincidence.
What do I mean, coincidence?
The sun is about 400 times wider than the moon, but it just so happens to also be about 400 times farther away.
Oh.
So from our perspective on Earth, they appear to be the exact same size in the sky. It's an incredible fluke. If the moon were a little smaller, the sun a little closer, we would never get that perfect magical moment where the moon just covers the sun and reveals the corona.
We're lucky to live in the era where we can see that.
We really are.
And just to cap off the sun section, we need one more scale comparison, because big doesn't mean anything in space unless you compare it to something we know.
The number is 1 million. You can fit 1 million Earths inside the sun.
1 million.
If the sun were a hollow gumball machine, you would need 1 million Earth-sized gumballs to fill it up.
Okay, keeping that scale in mind, let's move away from the fire. Let's take a tour of the solar system itself. Section 3.
The planetary tour. The weird and the wonderful.
So the source gives us the census. 8 planets, over 170 moons, and millions of asteroids and comets. And it defines a planet very simply. A ball-shaped object orbiting a star.
Which is a very polite and diplomatic way of avoiding the whole Pluto controversy, but we'll let it slide for today.
We will let it slide. So we've got the inner rocky planets and the outer gas giants. Let's look at the neighbors first. Mercury.
Mercury is the sprinter. It's the smallest, it's the closest to the sun. A year on Mercury is only 88 Earth days long.
Just whipping around that track.
It has to. It's basic orbital mechanics, Kepler's laws. The closer you are to the massive gravity of the sun, the faster you have to be moving sideways to avoid just falling in.
So if Mercury slowed down,
it would be coast. It would spiral into the sun.
Then we have Venus. Now, I teased this in the intro. Venus is the oddball, the rebel.
It really is.
Yeah.
In terms of size and mass, it's practically Earth's twin. But the text points out its very weird spin. Venus spins in the opposite direction compared to almost every other planet.
Okay, so on Earth, the sun rises in the east and sets in the west. We all know that.
On Venus, it rises in the west and sets in the east.
That's bizarre.
And it happens very, very slowly. A day on Venus is longer than its year. It spins incredibly slowly.
So why is it spinning backward? Did it just form that way?
The leading theory, and the text hints at the violence of the early solar system, is that it didn't form that way. Something hit it. A massive object, maybe the size of Earth itself, slammed into Venus billions of years ago and literally knocked it upside down. So from our perspective, it looks like it's spinning backward, but what's really happening is it's just spinning the right way, but it's upside down.
That is a headache just to think about. An entire planet flipped over.
A planetary scale catastrophe.
And then we have Mars, the red planet.
Red because of rust.
It's literally rust, like on an old car.
Literally iron oxide, the same stuff. The soil and rocks on Mars are very rich in iron, and at some point, billions of years ago, that iron interacted with oxygen and water.
Which strongly implies there was oxygen and water there to begin with.
Exactly. The rust is a fossil. It's the chemical ghost of a warmer, wetter past.
Okay, let's cross the asteroid belt. We are leaving the small, rocky worlds and entering the realm of the giants. Jupiter.
The king. It is larger than all the other 7 planets combined.
Wait, combined?
Put Saturn, Uranus, Neptune, Earth, Venus, Mars, and Mercury all in a bag, put them on a scale, and Jupiter is still heavier.
And yet, despite being this massive, bloated monster of a planet, the text says it spins incredibly fast.
Unbelievably fast. A day on Jupiter is only 10 hours long.
That's just dizzying.
Think about the physics of that for a second. It's a ball made mostly of gas and liquid that's 11 times wider than Earth, and it is completing a full rotation in just 10 hours.
So the centrifugal force must be insane.
Insane. That's why Jupiter looks striped. Those are cloud bands being whipped around the planet at hundreds of miles an hour. And it's also why the planet bulges at the equator. It's not a perfect sphere. It's a visibly squashed ball.
Okay, moving on to the other giants. We're going to save Saturn for a dedicated deep dive in a minute because it definitely deserves it. Let's talk about Uranus.
The one that got knocked over. The text mentions Uranus is tilted on its side.
The North Pole is basically where the equator should be.
That's right. If all the other planets are like spinning tops, spinning upright on a table, Uranus is like a ball that's rolling along the floor on its side.
And again, why?
The same answer as Venus, probably. Another massive collision. The early solar system was a cosmic billiards game, played by giants. Something big hit Uranus and just knocked it over.
And finally, Neptune. The windiest place in the solar system.
By far. The winds there are 9 times stronger than the strongest hurricanes on Earth, supersonic winds.
Which is strange, right? It's so far from the sun, there's very little heat energy to drive that kind of weather.
It's a huge mystery. Neptune is somehow generating this immense internal heat to drive these winds, and we don't fully understand how.
And the year on Neptune.
164 Earth years to orbit the sun just once.
Neptune was discovered in 1846.
Which means that since humanity first laid eyes on it, it has only completed 1 full lap around the sun. It just finished its first human discovery year back in 2011.
That really makes you feel how slow and vast the outer solar system is.
It's the deep freeze. Things move slowly out there.
Okay, I promised we would stop and take a closer look at Saturn. The source material dedicates a good chunk of space to this, calling it the ringed planet. This is our next deep dive section.
Saturn is the showstopper. If you have a backyard telescope, Saturn is the first thing you want to look at. It never fails to impress.
All right, so we're pulling up to Saturn now. Looking at the source material, I was really surprised by the description of the rings. I mean, from Earth through a telescope, they look like a solid disc, like a vinyl record or something.
They really do. They look like a solid continuous sheet.
Yeah.
But if we were to fly our hypothetical ship right into them, which I would not recommend, you'd see that as a complete illusion. It's a debris field.
The text says billions of pieces of ice, but are we talking about like snowballs, ice cubes? What's the scale?
It's a chaotic mix of everything. You have dust-sized particles that are basically a shimmering ice fog. But then right next to them, you could have chunks of water ice the size of a Volkswagen Beetle, or even as big as a 3-story house, all tumbling over each other.
A flying ice mountain.
Billions of them, all in orbit together. And they are moving incredibly fast. But what I find most fascinating, and the text highlights this, is the gap. The big gap between the 2 widest rings, the A and B rings.
The Cassini division.
That's the one. You see this obvious dark lane between the rings. It looks empty, but it's not just a random empty space. It's being actively kept clear by gravity.
Gravity from what? From Saturn?
No, from one of its moons. The moon Nemus. It's orbiting much further out, but its gravity essentially bullies any ice particles that drift into that specific gap.
How does it do that?
It's called orbital resonance. Any particle in that gap orbits Saturn exactly twice for every 1 orbit of Mimas. So Mimas gives it a little gravitational tug in the same spot over and over again until it kicks it out of the gap.
So it's like a shepherd dog keeping the sheep in line.
That is literally the astronomical term for them, shepherd moons. They use their gravity to sculpt and maintain the sharp edges of the rings. Without them, the rings would just spread out and dissipate over time.
And the planet itself. We mentioned Jupiter spinning fast. Saturn spins fast too, about a 10.5-hour day.
And because Saturn is much less dense than Jupiter, it's actually lighter than water, that rapid spin squashes it even more. It is visibly flattened at the poles and bulges at the equator.
Wait, you said lighter than water.
Yeah. If you could find a bathtub big enough to hold it, Saturn would float.
That is a fun mental image. A bathtub the size of the solar system. Now, we can't forget the entourage. The moons of Saturn.
This text says 62 discovered moons, though that number is always going up as we find more tiny ones. But the heavyweight champion of all moons is Titan.
How big is Titan, really?
It's bigger than the planet Mercury.
A moon that is bigger than a planet.
A moon bigger than a planet. It has a thick atmosphere. It has clouds. It has rivers and lakes of liquid methane. Titan is basically a planet in its own right. It just happens to be stuck in Saturn's powerful gravity.
That really blurs the lines of what we call these things, doesn't it?
It absolutely does.
Okay, speaking of moons, let's bring it much closer to home. Section 6. Our constant companion, the moon.
Our moon, the only other world we've actually set foot on.
The source asks a simple question. What is the moon made of? But first it tells us how it got there. And it was not a peaceful process.
No, not at all.
Yeah.
This is the giant impact hypothesis, or as some astronomers call it, the big whack.
The big whack, I like that.
It's descriptive. The theory is that about 4.5 billion years ago, when the solar system was still young and chaotic, a protoplanet about the size of Mars, which we've nicknamed Theia, smashed into the early Earth.
It smashed into us.
A cataclysmic planet-sterilizing collision. The Earth would have basically turned into a ball of molten lava. Trillions of tons of rock and magma from both bodies were blasted out into space.
And that debris.
Over time, that ring of debris coalesced gravity, pulled it all together, and it formed the moon.
So the moon is literally made of pieces of the Earth.
In a very real way, yes. It's made of the crust and mantle of the early Earth, all mixed in with the remains of Theia. And that's why the chemical compositions of Earth rocks and moon rocks are so remarkably similar.
Structurally, the text breaks it down just like a planet. Crust, mantle, and core.
Yep, it's a layered world. It has a tiny little iron core, a thick mantle that goes from solid rock to partly melted near the core, and then a thick, dusty, heavily cratered crust on the outside.
Here's a fact from the text that makes me feel a little, I don't know, lonely. The moon moves 1.5 inches farther away from Earth every year.
It's the lunar drift.
Yeah.
About 4 centimeters, roughly the same speed your fingernails grow.
Why is it leaving us? Is it our fault?
In a way, yeah. It's stealing our rotational energy. As the moon's gravity pulls on the Earth's oceans, it creates the tides.
Right.
That tidal bulge creates friction with the spinning Earth, and that friction ever so slightly slows down our planet's rotation. To conserve angular momentum, it's a fundamental law of physics, that energy has to go somewhere. It gets transferred to the moon's orbit, which pushes it a little bit higher and farther away.
So Earth is slowing down and the moon is speeding up and moving out.
Exactly. Billions of years ago, days on Earth were much, much shorter. In the distant future, they will be longer, and the moon will appear smaller and smaller in our sky.
Which means no more total solar eclipses.
Correct. Eventually, the moon will be too far away to completely cover the disk of the sun. We are living in this very specific, very lucky window of cosmic time.
That connects right back to that snapshot idea. Now, the moon is also the only place humans have actually walked.
Between 1969 and 1972, a total of 12 astronauts.
And the source goes into some detail about the conditions they faced. No air, no food, no water, and the cold, or the heat.
The temperature swings are extreme. In the shadow of a rock, it's minus 250 degrees Fahrenheit. Step out into the direct sun, it's plus 250 degrees, a 500-degree difference.
I love the breakdown of the spacesuit it gives here. It's not just a set of clothes, it's a pressure garment.
It's a personal spacecraft shaped like a human. It's got multiple layers. It provides pressure, air. The text says it takes over an hour to put one on properly.
And the big backpack.
That's the life support system. It supplies the oxygen. But the detail that always gets me is the cooling system. The text mentions water tubes that run all through the suit.
Why would you need cooling? I thought space was supposed to be cold.
Space is a vacuum, and a vacuum is a fantastic insulator. That's how a thermostat works. If you are working hard on the moon, jumping around, collecting rocks, you're generating a lot of body heat. But that heat has nowhere to go. There's no air to carry it away. You would literally boil in your own sweat inside that rubberized suit.
So they have to actively pump the heat out.
They pump cold water through tubes woven into the underwear right against your skin to pull the heat away from your body and radiate it out into space from the backpack.
That is just incredible engineering. And the text mentions a moon camp in the future.
It says bases within 20 years.
Mm-hmm.
It's an ambitious timeline. But with the Artemis program, we are genuinely looking at going back. Not just to visit this time, but to stay.
Moving from human exploration to how we actually get there. Section 7, space travel and robotics.
We have to talk about rockets. The physics of leaving Earth is just brutal. It's all about fighting your way out of the gravity well.
Escape velocity.
Right. You have to be going incredibly fast to escape Earth's gravity. If you throw a ball up, it comes back down.
Yes.
If you throw it faster, it goes higher before it comes down. But if you could throw it at 25,000 miles per hour, it would never come down. It would escape.
The Ariane 5 rocket, which is a real workhorse of the industry, hits 23,287 miles per hour. That's about 5 miles per second.
1 Mississippi, you're 5 miles away. 2 Mississippi, you're 10 miles away. It's hard to even comprehend that speed.
And the record for speed mentioned in the source belongs to the Helios A and B spacecraft from the 70s.
An incredible 157,000 miles per hour.
To put that in human terms,
Right.
that's like traveling from London to New York in 1.5 minutes.
It's absurd. But you have to remember, Helios achieved that speed by falling toward the sun and getting a gravitational slingshot. That helps a lot.
The mechanics of the rocket are described well here.
Mm.
The solid rocket boosters give that initial massive push, that's the heavy lifting to get off the ground, and then they fall away into the sea.
It's called staging. You don't want to carry around empty gas tanks. They're just dead weight. As soon as a tank is empty, you drop it to make the whole rocket lighter and more efficient. It's the only way to get to orbit.
But what if we want to go even further? To Mars! We send robots. We have to talk about the driving experience on Mars. We've got Curiosity, we've got Perseverance. These are nuclear-powered, laser-wielding, 6-wheeled super labs, so I have to assume they are just tearing across the Martian dunes, right?
If by tearing you mean moving at the speed of a drowsy snail, then yes, they are tearing.
The stats in the Smithsonian text are actually kind of painful to read. Top speed, 260 feet per hour.
Per hour.
That is not a car. That is barely movement. Why would you build a multi-billion-dollar robot and give it the engine of a lawnmower?
It's not about the engine power. It's all about the stakes and the time delay. Imagine you are at home driving a very expensive RC car.
Okay.
Now imagine there's a 14-minute delay between when you move the joystick on your controller and when the wheels on the car actually turn.
Oh. So I see a cliff coming up. I slam on the brakes.
And 14 minutes later, the brakes engage. But by then, your billion-dollar robot is already at the bottom of a canyon in a heap of very expensive scrap metal. There is no AAA on Mars to come and tow you out.
So they aren't driving it in real time?
Never. It's impossible. They painstakingly plan out a series of commands and upload them. Drive forward 2 meters, then stop. Turn 15 degrees right, then stop. Take a picture of that rock. The rover executes the commands, but it does it very slowly, thinking about it, checking for hazards with its own onboard computer. It moves an inch, stops, checks again.
It's extreme anxiety encoded into software.
Precisely. Because one bad command, one unforeseen rock, and the whole mission is over forever. And despite the tortoise speed, the tech on it is amazing. It has a laser.
A laser to zap rocks. For science.
It fires a powerful laser pulse that vaporizes a tiny pinprick of the rock's surface into a puff of plasma. Then a spectrometer on the rover analyzes the light from that plasma to figure out exactly what the rock is made of. It's chemistry at a distance.
Okay, so we have rockets going up, robots crawling around on other planets, but stuff also comes down. Section 8, space debris. Or, as the source more poetically puts it, shooting stars.
This is a great section for clearing up terminology. People use all these words interchangeably, but they mean very different things.
Right. Let's get the dictionary out. We have meteor, meteorite, shooting star, and fireball.
Okay, a shooting star is just a misnomer. It's not a star. It's a meteor. Simple as that. A meteor is the streak of light you see in the sky. It's the event itself, the act of burning up in the atmosphere.
So it's the phenomenon, not the object.
Exactly. A meteorite is the physical rock itself, but only if it survives the fiery fall and actually lands on the surface of the Earth.
So if it burns up completely, it was a meteor. If I pick it up off the ground, it's a meteorite.
You've got it. And a fireball is just an incredibly bright meteor one that's bright enough to cast a shadow on the ground, maybe even visible during the day.
And millions of these enter our atmosphere every single day.
Millions. But the vast majority are no bigger than a grain of sand or a tiny pebble.
So why do they glow so brightly if they're that small?
Pure speed. The text says they can hit the upper atmosphere at 45 miles per second.
Per second.
That's pure kinetic energy. The friction isn't what makes it glow, it's the compression. It compresses the air in front of it so fast that the air itself heats up to thousands of degrees and incandesces. The rock vaporizes almost instantly. That bright flash you see is mostly glowing air.
But some of them are big. The source mentions the big one.
The Hoba meteorite in Namibia. It's the largest single intact meteorite ever found on Earth. It weighs 66 tons.
66 tons. That's the weight of a battle tank. Did it leave a massive crater?
That's the really weird thing. No, it didn't. It's relatively flat on both its top and bottom sides. Scientists think that it entered the atmosphere at a very shallow angle and skipped along the upper layers, like a flat stone skipping on a pond.
So it slowed itself down.
It slowed down enough that by the time it hit the ground, it just kind of thudded. If it had come in at a steeper angle, it would have been a major disaster.
It's a good reminder that Earth is floating in a cosmic shooting gallery. We usually just see the pretty lights, but sometimes the rocks do land.
The dinosaurs know that all too well.
Which brings us to the final leg of our journey. We have officially crash-landed. We are back on the blue marble, Section 9, back down to Earth.
It's easy to forget that Earth is a planet, too. It has stats just like Jupiter or Mars. We just happen to be living on them.
So let's look at the stats. Shape, a globe. More accurately, an oblate spheroid. Circumference at the equator, 24,901 miles.
And the source offers a fun thought experiment. If you could walk the equator 247, how long would it take you?
It says a year, a full year of nonstop walking.
A full year. And that's assuming you could walk on water, of course.
Right, because geography is a thing. We have 7 continents. Asia's the biggest.
By a huge margin. 2/3 of the entire world's population lives on the continent of Asia. That's a staggering density.
And the oceans. You know, we call our planet Earth, but we probably should have called it planet Water.
Nearly 3/4 of the surface is covered by ocean. The Pacific, Atlantic, Indian, Arctic, and the Southern Ocean. And that water is the key to everything. It's the great buffer. It regulates our temperature and our climate. Without those oceans, Earth would look a lot more like Mars or Venus.
And finally, the spin.
Yeah.
The text mentions that the Earth is constantly turning, moving the land beneath our feet from west to east.
It's moving at about 1,000 miles per hour if you're standing on the equator.
Wow.
You don't feel it, of course, because the atmosphere and everything around you is moving with us. But if the Earth were to suddenly stop spinning and Nursery would send everything flying eastward at supersonic speeds, it would be the end of everything.
Okay, let's hope that doesn't happen.
It's very, very unlikely. Don't worry.
So we have done it. We have gone from the supermassive black hole at the center of the Milky Way. We've passed by those 13-billion-year-old stars. We watched energy struggle out of the sun for 100,000 years. We drifted away with the moon, crawled with the Mars rover, and finally walked the equator of Earth.
It has been a pretty comprehensive trip.
And this brings us to our final thought, the provocative thought for this deep dive.
I think it all comes back to time, to that idea of a snapshot. We talked about the sun's energy being ancient. We talked about the moon drifting away inch by inch. We talked about a star that's 13.2 billion years old. The version of the solar system we see today, the one that's described so beautifully in this book, is just a single frame in a movie that is billions of years long.
Right. It's not a static museum piece.
Not at all. If we were having this conversation a billion years ago, the moon would have been much closer and larger in the sky. The days on Earth would have been noticeably shorter. Venus might not have been flipped upside down yet.
And if we look forward,
If we could have this conversation a billion years from now, the constellations in the night sky will be completely unrecognizable because the stars are all moving, the rings of Saturn might be gone.
wait, the rings are temporary?
They are. We now know they are raining down onto the planet very slowly. They might only last another 100 million years or so, which is a blink of an eye in cosmic terms.
So the facts in this book are really just current events in the eyes of the universe.
That's the perfect way to put it. We are just incredibly lucky to be here right now in this specific snapshot of time where we can see the glorious rings, where we can witness a perfect total solar eclipse, where we can look up and see the Milky Way before our galaxy inevitably collides with the Andromeda galaxy in a few billion years.
That is a very humbling thought to end on. So tonight, if it's clear where you are, go outside, look up, find that faint milky band of light, that glittering wheel of our galaxy, and just take a moment to remember that you are standing on a wet, spinning rock, drifting through a universe that is vast and ancient and beautiful beyond all comprehension.
And try not to think about the cosmic shooting gallery too much before you go to bed.
Good advice. Thanks for listening to The Deep Dive. We'll see you next time.